Hello, everyone. My name is APOUL James, and my colleague is MuwanguzI Mercy. We are here to talk about the topic of attention-based knowledge distillation. First of all, before we talk of the attention-based knowledge distillation, we must understand the knowledge distillation concept. So when we talk of knowledge distillation in general, knowledge distillation refers to the process of transferring the knowledge from a large unwielding model or set of models to a single smaller model that can be practically deployed under real-world constraints. So knowledge distillation is performed more commonly on neural networks associated with complex architectures, including several layers and model parameters. Therefore, with the advent of deep learning in the last decade, its success is diverse fields, including speech recognition, of course, which we have seen several times, especially when we're giving in our passwords. Then image recognitions, that is sometimes we cite things around us using our phones. We just capture and then it recognizes the image and tells us. And then there is, of course, natural language processing, knowledge distillation techniques have gained proficiency for practical real-world applications. So in this case, we can let's talk about the graph that has actually been shown there that we are seeing. That graph is all about knowledge distillation. And it shows us that a small student model is learning, or it is trying to mimic a large teacher model and leverage the knowledge of the teacher to obtain the smaller or higher accuracy of it. At least it gives us the better accuracy from what it has learned from the teacher model. So when we talk more of the one we are seeing down, that one actually talks more of the diagram. The next diagram down is telling us more of, let us say, the types of knowledge that we talk about in this case. That means we have also to define, to understand what knowledge means in computer in this case. So in neural networks, simply knowledge refers to the learned weights and biases. So at the end of time, there is a rich diversity in the resources of knowledge in a large deep neural network. Typically, knowledge distillation uses the logics as the source of teacher knowledge, whilst others focus on the weights and activations of intermediate layers. So there are three forms actually of knowledge distillation as we are seeing in this diagram. That is the relation-based knowledge, and then there is we talk of response-based knowledge and feature-based knowledge. So when we explain them in details, if we are to go to the next page, it tells us that the response-based knowledge actually focuses on the final output layer of the teacher model, and the hypothesis is that the student model will learn to mimic the predictions of the teacher model in this case. So that is what the illustration actually tells us. And then when we are to explain the feature-based knowledge, so this is a trained teacher model also captures knowledge of the data in its intermediate layers, which is especially, let us say in this case, it is patterned for deep neural networks. So the intermediate layers learn to discriminate specific features, and the knowledge can be used to train a student model. And that is what we are seeing next. That is that one there in our diagram. So within our diagram also, there was relation-based knowledge, which is another type of knowledge or another form. So in addition to the knowledge represented in the output layers and the intermediate layers of a neural network, knowledge that captures the relationship between feature maps can also be used to train a student model. This form of knowledge, terms as a relation-based knowledge, is depicted as we have seen it there. So let's talk more of algorithms. Now we are going to talk of the algorithms that we use to train student models to acquire knowledge from the teacher models. One that we can talk about is the first one is adversarial distillation. So adversarial learning, as conceptualized recently in the context of the generative, let me say, adversarial networks, is used to train a generator model that learns to generate synthetic data samples as closely as possible to the true data distribution, and a discriminator model that learns to discriminate between the authentic and synthetic data samples, something like that. So when we talk of the multiple teacher distribution, now this one, a student model acquires knowledge from several different teacher models. Now the cross-model distillation. When we talk of the cross-model distillation, here, the teacher is trained in one modality and its knowledge is distilled into the student that requires knowledge from a different modality. So now there are other forms of knowledge that, other forms of algorithm that we actually talk about here. And those other forms are the graph-based distillation, attention-based distillation, data-free distillation, and quantized distillation, long-term distillation, and neuroarchitecture, site-based distillation. Now, in this case, what we are actually going to talk about here mostly is the attention-based distillation, attention-based knowledge distillation, which is actually is based on transferring knowledge from future embeddings using attention maps. So let's go to here. First of all, let's talk of the limitations. Why did we bring in the modern knowledge distillations other than using the traditional knowledge distillations? Well, there were some limitations that were seen in the traditional knowledge limitations, which we are actually seeing on the screen right now. The first one is the informed bottleneck. So what is the informed bottleneck? Here, there is often a loss of important information during the distillation process, as the smaller model may not capture all the nuances of that larger model, of course. So that is informed bottleneck. So the smaller model is informed. So instead of capturing all the information that will not be useful to it, it will only pick the information that it thinks it is valuable to achieve its work. So when we go to the computational overhead, now the distillation process here can be computationally expensive. So requiring significant resources to train the smaller model using the outputs of the larger model. Yeah, this is actually expensive. Therefore, that is the reason why we came in with these other types of knowledge distillations. So another limitation or another challenge that was faced in the traditional knowledge distillation was sensitive. It was sensitive to hyperparameter choices. Yeah, now the performance of the distill model can heavily, let us talk of this case, depend on the choice of the hyperparameters. So making the process more complex and time consuming. Therefore, we require better knowledge distillation forms. Another one we can talk of it is that it requires large amount of labeled data. So when we talk of this, requiring large amount of labeled data, in this case, it tells us that effective knowledge distillation often needs a large data set, and actually a large data set with labels which may not always be available or easy to obtain. Hence, we had to switch to better forms of knowledge distillation. There was also limited scalability in the traditional the distillation methods or knowledge distillation. So, for example, scaling the process of different tasks or larger models can be challenging. That is making it less flexible in diverse applications. These were actually the limitations that actually brought about the use of the current knowledge distillations. So allow me to invite my colleagues to proceed from there. Well, attention mechanism, before I continue here, when we talk of the attention mechanism is, it was inspired by the human cognitive processes of focusing on important information. That is, for example, it is used extensively in transformer architectures like BAT and vision transformers. And it also helps models allocate more weight to significant features. That is now the attention mechanism. Please allow me welcome my colleague to proceed from there.
Hello everyone, my name is Mercy Mwanguzi and I'll be taking you through the attention-based knowledge distillation. So just the way you'd be in a club and you're having a conversation with your colleague and you try to focus on what your colleague is saying and you ignore everything else, the other noises around you, that's what happens in the attention-based mechanism. So when we bring in the knowledge distillation, the attention-based is brought into the knowledge distillation to enhance what the traditional distillation methods could not do. And it does this by incorporating attention maps. So the attention maps, they transfer knowledge from the teacher to the student, not with just the logists, but it also uses attention weights. And with the attention-based incorporated with the knowledge distillation, there will be improved interpretability of the model, and there will be improved generalization of the model. As you can see in the image here, we have a fox, and for the model to be able to determine that this is a fox, you're having an attention map where it has specific features it's looking at to determine that this is a fox. So how it works, it extracts an attention map, and this attention map is supposed to represent where the model focuses in the input. And this has a formula, as you can see, where the Q is the query matrix from the teacher, the K is for the key matrices from the teacher, and the W is the land weight matrices. Then after it extracting the attention map, there's going to be the student model training. And in the student model training, this involves fine-tuning of the student model using the combined loss function. Then the training data that is the same as that has been used in the teacher model is passed through both the models, and then the student tries to mimic what the teacher model has been doing. Then after that, the next process will be the loss optimization. So here we are trying to ensure that there is less loss in the accuracy of the model. And how we do this, we have what we call the output alignment loss, which minimizes the difference between the logist of the teacher and the student model. And then we have the attention alignment loss, which focuses on reducing the disparity between the attention maps of the teacher and the student model. And we have the techniques of mean squared error and the callback neighbor divergency. Then after loss optimization, we have the next step, which is attention transfer. And there are different types of transfers. We have spatial attention transfer, channel attention transfer. Yes. Then moving on, where we apply the attention-based knowledge distillation, we have in natural processing language, whereby the model is supposed to focus on only what is being said, and from that we are able to train models on the font. Most times the traditional knowledge distillation techniques that are there, they cannot be compatible with mobile phones. But with attention-based in place, it can be used on phones. Then we have computer vision, where the models are able to determine the object presented to them. Then speech recognition, whereby the model is supposed to only focus on what an individual is saying and ignore the noise around the person and be able to give feedback according to what the person has said, just as when you're using Siri, when you're using the Google speech feature. Then we have machine translation, whereby the model is able to translate things that the machine is doing into what a person can understand or what the person wants. Then we have recommendation systems, whereby the models are trained to give feedback to a person according to what they have put in, maybe meal recommendations, medicine recommendations. Then moving next to the benefits of the attention-based knowledge distillation. It's a better feature representation, but you can easily know that this feature relates with this, and it's important for the model to learn. And there is improved model interpretability, where you can easily understand what the model is doing because you're focused on specific things. Then there is more efficient knowledge transfer, because here now the model is not having a lot of information, only the specific features have been transferred to the student model, so it doesn't have a bottleneck of information. Then there is enhanced performance on complex tasks. Since there is attention being used, the model is able to easily implement the complex task because there is reduced computational overhead. Yes, the challenges with this type of mechanism is the attention map misalignment, in that if the student model and the teacher model attention maps are not aligned properly, there might be inaccuracy in the model. Then sometimes you can have computational overhead where you need memory efficient computers to be able to train the teacher model so that it can easily transfer specific things to the student model. And the architecture design of such a type of technique might be hard to implement. So moving to our code implementation, I'm going to invite my colleague to take you through that.
Good evening once again. Well, we are actually explaining this, the code implementation for attention-based knowledge distillation. Well, when we implement this, we are going to let's discuss the code fully. We began with the installation of the libraries, or let me say the dependencies. And then the main library that we actually installed was the touch, alongside the touch vision. So the touch, what is the use of the touch in the first place? This one is just a deep learning framework that is used in deep learning. It is just a framework used in deep learning. So there's another dependency that we imported from the neural network, which is the touch.nn, which defines the neural network itself. And then the touch optim is an optimizer, and we have used in this case the Adam optimizer. So another one is the touch.nn.functional as F. Now this one is extra functions like activation functions and losses. So there's now the touch vision models. This one actually is a pre-trained model. For example, ResNess. It is just a pre-trained model, the model that has already been trained. Now let's talk about let's talk about our first model in this case. So our first model, we are going to use the ResNet 18 as the teacher, for example. And then when we use that one there, now the last fully connected, we remove the last fully connected network because we only need the feature maps in this case. Then here we ensure that the model, teacher model.eval, we ensure that the model, of course, doesn't update weights when we are running. That is what the .eval means. That is the function for it. Now let's talk of our next model, which is the student model, in this case, the smaller CNN. So we use the light-weighted CNN as the student model. And then our first convolutional layer is output is served as the attention map, as we can see in the diagram. Attention map, yes, just up within the def forward function. So now after saving that, now we go ahead and we are going to use the first function up, the one for defining the losses and the losses function. So when we define it here, we define the attention as our function here, attention loss. And then actually the question that we should be asking ourselves is, why is attention important? So it is just simply means that instead of us just training the student model on levels, we focus it mainly, we actually force it to focus on the same image region as the teacher model. Why? So that we achieve the better performance out of it without reading a huge network, something like that. So in this case, how do we make it work? Yeah, we normalize as we are seeing it there, we first normalize the attention maps to make them comparable. Then after normalizing now, we compute the mean square error. We are actually in attention loss definition. That is what I'm explaining. So we compute the mean square error between teachers and the students' attention maps. Now the next one, after us defining and of course the attention loss function, we go ahead and train the student model. When we are training the student model, of course, we imported already the optimizer, which is the Adam optimizer, and we mainly use it to adjust the weight efficiently, simple. So the next thing is to standardize the classification loss, which we use down there in our next criteria, which is cross entropy loss standard. That is to standardize the classification loss. Our next thing is actually to train. Let's train our old function now. Yeah. So when we are training our old function, we move models and data to GPU for faster training, of course, and then we compute two losses. In this case, that is the classification loss, which ensures that, so that we ensure the correct predictions. That is the meaning of the classification loss. Now the attention loss, it makes the student mimic the teacher's attention, exactly, just mimicking. So like if the student write, for example, if the students, we are now talking outside this code, if the teacher writes letter A in class, let us say for nursery school, the student will mimic the teacher the way the teacher was writing letter A. So that is what we are meaning in this case. So after that, then we combine the both losses. So how do we do this? We calculate the total loss in this case, which is the cross entropy loss plus 0.5 times the attention loss. This is the weighted sum of, let us talk of both losses, which is the total loss in this case. Yeah, so now this is what the entire code is all about. We don't need anything to talk about here, and then we wait to see the outcome. So this is how we implement the code. Thank you.